Hello everyone, welcome back to my YouTube channel. In today's video, I will show you how we can properly set up the thermal conductivity for cylindrical battery cell. It is extremely important to properly set the thermal conductivity for cylindrical battery cell, otherwise it can lead to incorrect temperature distribution. By the way, in the description I have included Amazon links for some good CFD books and useful tools. Using these links also support the channel. You can also support the channel via PayPal. For the demonstration, I will set up a really simple case starting with 3 battery cells, nothing else. For that, I am just making a circle at the center and setting the diameter of 21 millimeter because I will be simulating 2170 cylindrical cell. I will not go into the detail of geometry and meshing, but we will see how we can set up the thermal conductivity. Let's go to 3D mode and I can create a pattern for this battery cell. Let me click on this one and then pattern. I want to have 3 and at a distance of, let's say, 50 millimeter. I have 3 cells. I will click this green tick and now I will extrude in both direction. And it is 70 millimeter. I have 3 battery cells now. We can move to meshing. I will quickly give them the name cell 1, cell 2 and cell 3. I will also give name to the wall so that I can apply convection. Wall 1, wall 2 and wall 3. Actually, I am having these 3 cells and I want to apply different thermal conductivity on these 3 cells, and then you can see the effect of the thermal conductivity on temperature distribution. And for the purpose of meshing, I am just saying the meshing is 1 millimeter cell. That's it, and we can generate meshing. Meshing looks fine. We can quickly move to Fluent because there is the actual work. Before moving to Fluent, let's understand the thermal conductivity of cylindrical cell. Here you can see that's how a cylindrical cell is made of different material layers. The different material layers, they are stacked. One is anode, cathode, separator. They are stacked in terms of layers and they are rolled and then packed inside the cylindrical cell. It means we have 3 different directions. One is the axial direction, which will follow these lines. Then we have the radial direction, in which case the heat has to pass across these layers. And then we have tangential direction. It means in that case the heat will flow in circular path and it will follow these layers. The thermal conductivity in axial and tangential direction will be same because in that case heat will flow along the material plane. But in radial direction heat will flow across the planes. It means in that case the thermal conductivity would be different. That's why for cylindrical cell we use cyclic orthotropic thermal conductivity. Now let's see how we can apply in Fluent. We are in Fluent and in model it is steady state and energy equation, yes, we will say on, and then I have to define 3 different materials for cell 1, cell 2 and cell 3. Let me call them cell 1, remove this one. So I am not changing density and specific heat, only thermal conductivity. For cyclic orthotropic thermal conductivity, you have to go down and there is cyclic orthotropic thermal conductivity. Select this one. 1 minute please. Yes, now we can see properly, and let's go again to edit, and we have got this window. Here it is asking the axis origin. For each cell you have to define the origin of the axis. This cell is at the 0 0, so in this case it will be 0 0 and 0. Axis direction is Z direction, so in that case we have to put 1 at C. If it would have been in X or Y direction, then we would have done like that for Y, 0 and 1. But anyway, it will be 0 and it will be 1. Now we have three components. Radial direction, as I have shown you, radial is in the radial direction, and I told you it will be the lowest because in that case the heat has to pass through those planes. Normally it is in the range of 1. The tangential and axial, they are in the same order and they are in the order of 20. So let's put 20. And that's it. We can say okay, and we can say change create, override no. Okay, we have defined for this one. Now let's define for second cell. Let's call it cell 2. Remove this one. Again cyclic orthotropic. The axis origin for this cell Y and Z are 0, but X is 50 millimeter apart from the origin. That's how I set in space claim. So I will write here 0.05 because it should be in SI unit. Radial is 1, tangential is 24 and axial is also 24. Cell 2, okay. Change create, overwrite aluminum no. Let's call cell 3, remove this one, and let's keep this one as a constant for cell 3 and we will see the difference for all three. Override aluminum, yes, and we have defined all three materials. Now we can define our heat source. Source term is here, source term I am saying 100,000, okay, and material is cell 1. Apply and close. I can define one by one for all three, or I can copy paste from cell zone 1 to cell zone 2 and 2.2. I have to select these two and copy. It means the same boundary condition from cell 1 has been copied to cell 2 and 2.2. Close, but still we need to change the material. Okay, for cell 2 first let's keep this one as a cell 1. It means we are using the same origin for thermal conductivity as of cell 1, and let's see what will happen. Apply and close, and this one is cell 3 actually, and let's say it is cell 3. Apply and close. Now let's go to wall. We want to set the convection boundary condition on the wall. Heat transfer coefficient 100 and freeze stream temperature, let's keep it 300. Apply, close. We will copy to wall 2 and 3 from wall 1 to boundary zone wall 2 and 3. Copy and close. It means same boundary condition has been applied to wall 2 and 3. That's it. Our simulation setup has finished for this particular example. I have changed the, not this one, the residual to -10, and then we can set the number of iteration whatever you like. Let's set it 200 and see how many iteration it will take to converge. Initialize and simulate, and let's simulate. Okay, now let's see our temperature distribution. That's how our temperature distribution look like. For cell 1 it is pretty good. That's what I was expecting. At the center higher temperature, and towards the end it will be lower because we have cooling on the outer surface. For cell 2 it is quite different. As I mentioned, for cell 2 we are using the thermal conductivity of cell 1 or the origin of cell 1. It means for this one the origin is over here, and tangential thermal conductivity will have much bigger circle around this origin, which will be going like that. So that's why we are having like this the temperature distribution. For cell 3 it is constant, and you can see it is pretty much same overall because 24, which is quite high. Let's insert a plane at the center, ZX plane, yes, create, close, and we want to see only through this plane. And you can see the temperature distribution, it is quite different for all three, and it makes sense as per the thermal conductivity. Now let's change the thermal conductivity for this one and see what will happen. For that we just need to go to the cell zone condition, cell 2, and I will change material to apply and close. Now I can run, initialize and run, and you can see the temperature distribution will be same as of cell 1. It will be pretty fast. You have already seen, but let me bring it back. Now you can see the same temperature distribution as in cell 1, and that's how it should be in cylindrical cell. If you do not set your thermal conductivity properly, it means your temperature distribution will be off. Yes, and that's true. If you have, let's say, 100 cylindrical cell, you have to define material for each cell separately. And that would be a quite hectic job if you would do manually from here for each material one by one. For that, I have created a video. You can use the journal file or the text user interface. You can check on my page. I will also provide the link in the description. That will help you to set up your thermal conductivity for whatever the number of cells pretty fast. It means if you have, let's say, 100 cell, it will hardly take 1 minute to define 100 materials. But of course, for that first you have to write the script or the journal file for that, but you can check that. Anyhow, that's it for today. I hope you found this tutorial helpful. Thanks for watching and see you in the next video.